equation.
Ladies and gentlemen, the Drake equation part 2 is about to start. Gary Loveridge gave a very brief overview, so he's going to have to talk very quickly to fit everything in this hour. And Dr. Bob as well. So, ladies and gentlemen, Gary, Dr. Bob. Great.
Is there anybody here who wasn't here yesterday?
Really?
Okay, you're screwed. So what we did is yesterday we talked about the history and why the Drake equation. Now we're going to look at some of the individual factors of the Drake equation. Switched on. So it's mostly how many alien civilizations out there. So the first one, that's the equation. Okay.
Pretty.
It's very pretty. Is the other door open slightly? Still?
Yes.
That's right. Yeah, most of you have seen that one. It's a very pretty one. So, the first one, just make sure I've got this. Right, that's the nub of it. That's the point of this whole equation, is how many civilizations can we detect? How many can we communicate with? Are there lots, or are we alone in the universe?
How many is it? Bloody hell, not communicating with that load.
Exactly, that was one of the things from like yesterday. So the first part, so that's the N on it. The first part is the average rate of star formation. So it's how many stars are being formed every year, because that's because that would determine how many stars we have to look at. We know this. This is known. We've calculated this. It's been tweaked and corrected. Later on we'll start putting numbers in, but this is the easy one because we know this. This is probably one of the only factors that when Frank Drake came up with this equation back in 1961, he knew, because you just look at the stuff. What fraction have planets?
Do the planets turn up at the same time as the stars?
Yes.
Oh, they do.
They're usually formed about the same time. They come from a big ball of, flat disk of gas and dust.
Yeah, what's a couple of billion years between?
Yeah. So when you're talking billions of years, yeah, they come about the same time. But yeah, they're usually forming about the same sort of time. So when, in 1961, they suspected that stars had planets around them. So there's the phrase exoplanets, which, for those who don't know, means any planet that orbits a star that's not ours. So any planet outside our solar system. And they can be everything from big, giant, super gas giants, all the way down to much smaller. But at the moment, we can't detect the tiny ones. But we're working on it. So this was just a theory. Now, thanks to wonderful science and some really amazing probes like Kepler and Gaia, we have detected over 5,000 confirmed exoplanets. Over 5,000. Things like TRAPPIST-1, that they detected that 7 planets, all of them are terrestrial, which means they're made of rock rather than gas. All of them potentially could have life. Some of them are definitely in that region. So some planets, for instance, our closest neighbour, Proxima Centauri, definitely has a planet there. We know that, and that's quite an interesting one, and we'll talk about that later. But now, and there's several more thousands where they've looked at the data and gone, oh, that could be an exoplanet. But we're not sure yet. We need to crunch the data and look at them again just to confirm. But definitely over 5,000 at the moment.
And those are only the stars we've bothered to look at.
Yeah. Is it worth me doing a bit on how we find the exoplanets?
No, because it'll take too long.
Okay. that could be next year. Okay.
That could be up.
Yeah.
That's a whole talk.
So the next one is, how many of these can support life? Well, life as we know it requires 2 or 3 main components. One of them is liquid water, because all our the other one's carbon. Okay, our life as we know it. Carbon because it forms so many molecules.
Especially rings.
Yes, it produces the core of everything that all the organic processes. The organic means it's got carbon in it. So because of its nature, it's an unbelievably versatile element.
Yeah, carbon is really good at bonding to other carbon atoms and to oxygen and hydrogen, but not in a way that you can't rip the molecule apart and build it into something more interesting. Whereas silicon, once silicon and oxygen has met, I've never ripped them apart. Yeah. So quartz lasts forever. Biology is messy and forms and reforms and does different things with the molecules.
So, and something like about 80% of all chemistry is organic chemistry with carbon in it. It's really annoying because I hate organic chemistry. But in order for and all our biological processes happen in a liquid environment. You are mostly a squishy bag of mostly water. So everything inside, all the chemical processes, all happen in a liquid environment. So water is so important to us. And in order to have liquid water, you need to have them in a certain distance from a planet, from a star. So this planet needs to be in what we call the habitable zone or Goldilocks zone. It is an official name, scientists, astronomers use. It means that the planet isn't too hot and it isn't too cold. To give you an idea of in our solar system, Venus is in the slightly too hot end of the habitable zone. Mars is in the slightly too cold at the end of the habitable zone. We sit just right. Do you want to add anything more?
So why do they think there might have been life on Mars?
Because there used to be liquid water.
Right.
We know for a fact now there used to be liquid water.
And also the sun has not stayed the same intensity as it is now. In fact, global warming might be worse than you think it is, because there's this thing called the faint young sun phenomenon, where it wasn't as bright before, but the planet was hotter, and Mars has Mars currently has a very circular orbit, but it might have been elliptical, in which case it might have been more seasonal. There's various geology and astronomy things that Mars might have been more hospitable back in the past, but it isn't now.
We know there was running water on Mars because the probes that we've sent, both orbiting and landers, have found evidence that indicates there used to be water. Which is why we're looking for life, because if there's water, maybe there's life. The other option is, we're talking about life as we know it. Titan, as I said yesterday, has a liquid surface, has liquid oceans, but they're made of methane. But that could be, maybe, enough liquid for biological processes, maybe not as we know them.
There are bacteria that do not like oxygen, they can't cope with oxygen, down in deep sea muds, where all the life that you're familiar with, plants create oxygen, animals breathe oxygen and believe out carbon dioxide, take the carbon dioxide, oxygen, so you've got something that produces oxygen and uses carbon dioxide, something that uses oxygen, produces carbon dioxide, and they're complementary, and it's a lovely cycle. There are what they call methanogens, things that create methane, and methane users, and there's a little cycle of bacteria down there. So in theory, maybe on Titan, but how much of what the bacteria on Earth do rely on Earth temperatures, Earth pressures, other Earth chemistry that's going on with, hydrothermal vents and sulfur and other things. But we know life can use methane as its main substance, methane rather than oxygen and carbon dioxide.
Yeah,
Our
Titan,
type of life,
Titan is very cold, which is why the liquid methane is liquid. The water ice is on Titan. What we consider water ice is rocks, and they're as hard as rocks. If you go out to Pluto, the water ice there make up granites like mountains. So ice gets very hard as it gets cold. Also, I've discovered there's about 7 different forms of ice. which I've done.
Yeah, different crystals.
Different types of ice.
Yeah,
Yeah.
put the
Yeah.
cursor on the crystals,
Okay.
do different
So,
things, yeah.
Next one, we're over to you now.
Yeah, are we? Okay.
Yeah.
Excellent. Okay, so another aspect of the dream equation is how many, we've decided there are planets out there, how many of those planets which are in the Goldilocks zone and have life manage to get intelligent life. And here we have lots of lovely examples from science fiction of intelligent life. And now, there's the bit where I have got opinions. So, next slide, please.
Next slide, please.
I'll try and pretend I'm Chris Petty or whatever. So, the Drake equation kind of assumes this, that you learn how to bang the rocks together, to quote Dr. Adams, whether we have 2001 banging the bones together, and as soon as you've done that, it is inevitable that you get a high-tech civilization with machinery and the ability to transmit a signal which aliens would be able to detect. However, can I have the next slide, please? Intelligence. On Earth, intelligence has evolved multiple times. Here are some current examples. But the quick-witted amongst you will notice that none of them have built a civilization and are transmitting radio signals. So there's being smart doesn't necessarily mean you can build a civilization. And I think there are some factors missing from part 5 of the Drake equation. They need 5.1, 5.2, 5.3. So it's if there's the Goldilocks zone, if there's life, if life is becoming intelligent, and then there's going to be another if, which I am going to prattle on about now. So are you all familiar with those animals? And
No, what's the brightly coloured fish thing?
that's a mantis shrimp.
A mantis shrimp?
Yes, which are very, very smart and good at problem solving. We've got octopus, elephant, corvid, so I've got the magpie up there. Many of the parrots, that's a bonobo, pygmy chimp, and a cute dolphin with its baby. Next slide, please. Right, so in order to have build a radio telescope and send out signals, or build a radio station or a TV station that accidentally send out signals, you have to have all sorts of things. Octopuses are what's known as semelparous, the same as salmon. They spawn and they die. A mother octopus lays her eggs, looks after her legs. She gets to see the first of her babies hatch, and then she kills over dead. Any experience, if she has invented the radio telescope, tough luck, the next generation of octopuses are going to have to come up with the physics and the engineering and so on from scratch. There's no overlap of generations. There's nothing passed on. So octopuses are really smart, but they can't do it unless Adrian Tchaikovsky's books, Children of Ruin, there's genetical engineering goes on to get over the gap. Mantis shrimps, they do look after the babies a bit more. They look after the eggs and are very defensive about them and so on. But once they hatch, they float off into the plankton, and mum and dad never see them again. So again, there's no overlap of generations. You can't pass on the so they're not social creatures. So they are smart. They've definitely got intelligence. Some octopuses, types of octopuses use tools, but they can't make a radio telescope and send signals. So they are off our... Oh, so next. The next thing you need is... You might not think about this, but our civilization requires a lot of division of labour. Everything from, your medieval village where someone was the potter and someone was the blacksmith and someone was the farmer and someone made the shoes and so on. Well, most animals, every animal has to know every skill in order to survive. Maybe only the females raise the offspring, but that means mum is teaching the sons how to be males as well as teaching the daughters how to be female. So you need division of labour, and you need it very, very specialised. Okay? So some creatures, if you're solitary, you can't do that. If you don't have a social system where you support each other and do different tasks. So some creatures do, like lions. It's the lioness's job to defend the territory, do the childcare, do most of the hunting. It is the lion's job to defend the lionesses from other lions, do a bit of the hunting, and so on. And some lionesses are rubbish at hunting, but they're great at childcare. And some lionesses are rubbish at childcare, but they're great at defending the territory. So you can do this in other animals apart from us to get this next. Oh, there's the lionesses. So the other thing is, another thing about lionesses, that's two prides of lionesses having a massive punch-up over who owns that scrap of land. You cannot build our sort of civilization if you're territorial in the biological sense of the word. Now, you might think humans are territorial because we use the word in commonplace, yeah, but we're actually possessive. And sometimes we're possessive about land, but we're not. A biological territoriality, you stay in your territory for life. You never leave it unless someone else drives you out of it. And once you've been driven out of it, that's it, you're on the scrap heap, you're dead. So they are, you will see hyenas fighting lions over food. You will never see hyenas fighting lions over land because they're different species and they're not getting the same signals. So if you're territorial, you can't do what these people are doing in that lovely kind of Bronze Age picture there, which is trade with your neighbours. In our ancestry, the Neanderthals, they can tell that bits of flint and bits of shell and things that the Neanderthals are using, the stuff that's left behind, the archaeological, none of it moved more than 30 kilometres from where it originated. So the flint is dug out of the cliffs here, it never goes more than 30 kilometres. That's as far as it got transported by people. They're in this little patch of land. As soon as we rock into prehistoric Europe, stuff starts moving on average about 120 kilometres. They're finding, carvings on whalebone of a seal 120 miles inland. People are trading and things. And that's because if you rock up to a place where you've never been before and you see some people, you might throw spears at them and be mean with them, but you might go, I've got some hides, do you want to swap it for that flint? And so on. And to be technological, you have to trade. There's no chance in hell that every single resource to create a television station, a radio mast, or kind of the food that you need to feed the canteen workers and the cleaning ladies in the astronomy lab, is all in your little patch. So there's certain things, not just intelligent, you have to be non-territorial, have overlap of generations, and be prepared to split the work up between everyone. Because you can't be a radio astronomer and a miner and an engineer and a farmer and and the guy that drives the bus to get everyone to work. You can't be that all simultaneously.
Unless you write some really, really bad fanfic.
Yeah, unless you have the planet of the Mary Sues, where everyone is brilliant at everything. So I think there's a few steps in the Drake equation that are missing. So I think, let's see, in terms of the fossil record, when the conditions, the gap between Earth being, they've stopped the bombardment and Earth is actually capable of supporting life, and when we actually get a chemical signature in the rocks to say there was life, is actually really quite short, geologically speaking. It's about, what, a quarter of a billion years? Nothing life. And that may squeeze down because we just haven't looked in the right places and found the signature. So I think life is really easy if you've got the Goldilocks thing. Intelligence is obviously worth having because lots of things involved it, but it has to be a very specific type of intelligence in order to go, hey, maybe we'll send a radio signal, rather than everyone just sits in their own little patch and goes, grrr, all the strangers, yeah. Next. And, okay. Oh yes, that's...
Just say, it's not only got to be have the intelligence, you've also got to have the physical ability to do something about it. I mean,
Yes.
Dolphins are extremely bright, but it's not much you can do without hands.
Yeah,
Or
dolphins.
something of the
Yeah, dolphins do a bit of tool use, but it's like picking up a thing in their mouth
Yeah.
and sticking it on the nose and using
Yeah.
it to.
Can't manipulate
And
one.
smelting metals underwater is really difficult. Yes.
Reason we rule.
Yeah, we have opposable thumbs and we live on land.
Really cats don't.
So, for instance, those are our two closest relatives. There's the pygmy chimp, and the one that's looking a bit more fierce and psychotic is the common chimp. And pygmy chimps, if two tribes of common chimps, two clans meet on the border, there will be a massive punch-up and there will be severe injuries and often they kill each other. If two bunches of bonobos meet up, the first recorded instance of this is the two turned up at a clearing and the two groups of apes sat and looked at each other and the anthropologist that is waiting for the huge fight to happen and they looked at each other and then the two matriarchs wandered into the centre of the clearing and shagged, so they had lesbian sex, and that solved the dispute and the two groups just sit and do their own thing. Because bonobos are they're not aggressively territorial. The groups have kind of ignored each other apart from the babies. They've played together, but we're probably descended from something a bit more bonobo-like, less public shagging, but more settling disputes in a sort of how do you do, and not the chimp way where if they're just psychotic. So my candidates for becoming civilized are African elephants because they nomadically wander around and aren't quite as bonobo-like things. So I've looked at all quite a long time.
Right.
There we go.
So, what fraction? We mentioned some of the problems yesterday. I'm not going to cover them again. You need to see the video on YouTube when it goes up. But radio signals, so we're now looking at that technology, that leap. And a lot of it, as Amanda said, is the learning. The reason we've developed these things are because we've developed on previous people's works. You know, what Isaac Newton said, I find great because I stood on the shoulders of giants. That's quite right, you work on development. By the way, the one on the left is quite famous, that's the Australian Parkes telescope. If anybody's seen the film The Dish, that's that one. And that is the one that received the signals from the moon landing. The one in the middle is the half-kilometre telescope, which is in China. That's 500 metres across. That's a big bugger. It's basically, they did what they did in Arecibo, but on acid. They just carved a chunk out of a mountain side. It's in the middle of nowhere in China. They just carved a big bowl out of the mountain sides. So it is actually about half a kilometre across. And the other one is just another pretty one. But radio signals is mostly what we're looking at as we discussed the complications and the advantages of using radio signals. Probably the next one is the most important one. How long do they release the signals? And that was a question, something was raised yesterday, is if they're only able to release the signals for about a couple of years, or the civilization doesn't exist when we are, we're not going to detect them. If, however, they manage to overcome, so if they wipe themselves out in some sort of apocalypse, we'll never pick up their signals. If their civilization is only able to do 50 years of communication, our chances of picking them up are small. However, if they get a utopia and they can send signals out for 1 million years, that increases our chance. That L right at the end of that equation is probably the most important one in reality. Because it's all about how long can they communicate. So,
and I pointed out to Gary, the civilization in the middle is going to have an apocalypse because it's AI-generated art, and if you look at the things on their airplanes, they're not very, on the planes people have got, it's all gone a bit pear-shaped.
yeah, I quite like the images, the way they blended as well.
Yeah.
That was pure fluke. Okay, so let's put some numbers in. Let's see if I can earn my Nobel Prize. Martin's not here, so he can't argue. So, first one, Oh, we talked about attenuation of signal, and we talked about that yesterday, the inverse square law and how everything gets
Yeah,
fades
for
as they
the
go out.
folk that weren't there yesterday, a drop of water has fallen in the pool, and you can see the ripples and how they get smaller the further they spread out. That's because the energy has gone in, but the wider it goes out, you know, the less signal you're going to be getting, because it's spreading on it bigger and bigger and bigger already.
And that's what the diagram on the left is supposed to illustrate, the fact that the signal.
So,
And it's what we call the inverse square law, because every distance is 1 over the square of the distance. So at r it's 1 over, it's 1, then it's a quarter, it's a 9th, 16th, 25th, etc.
yeah, so the further away you want to be heard, the louder you've got to shout.
Yeah. So, star formation. We know this. It's about 1.5 to 3 stars are formed in our galaxy every year. Usually, in our galaxy, it's in the spiral arms. If you look at the pictures of the galaxy, definitely not photographs of the galaxy. At least not ours, anyway. I've seen that. This is a photograph I got. No, it's not. But we've got the Andromeda galaxy, which we can photograph. So all the star-forming regions are in the arms.
When I worked for the BBC, Joe, who sat next to me, I've got a phone call from a producer, and they wanted a photograph of the Earth taken from the moon, and it had to be BBC copyright. Yeah, we'll just build a Saturn V and...
The advantage of it is you can use NASA stuff,
Yeah,
because NASA stuff is not copyrighted.
Yeah, we
It's all public domain.
said to do, yeah, tell them it's all copyright free and the BBC hasn't been to the moon.
Yeah. My Chromebook was a photo. The picture has a picture at the Artemis 1, where it was at its furthest distance. It took a picture of the moon and the Earth in the same. My favourite picture.
Yeah.
But yeah, NASA stuff, because it's publicly funded, none of their stuff is copyrighted. It's all public domain stuff. It's one of the many advantages of working for government stuff.
It's American government stuff. It's just the same with the US Geological Survey and the US National Park Service. British government stuff is copyright to Their Majesty's government, and you cannot use it for free.
Yeah, but the US government, because it's publicly funded, it's
their copyright law is different.
Right, so, yeah, we know it's about 1.5 to 3, because we've studied it, star-forming regions, we've seen it, you know, we're not watching it in real time, because that takes millions of years, but what we're seeing is different stages, and we can go, oh, that's turning into that, that's turning into that. And in a nebula, you usually have lots of different stars at different stages that are developing. Have planets, as we said, exoplanets. Pretty much we're finding almost, not all of them, but most of the stars we're looking at, that we've looked at closely, have at least one planet in orbit. So we're getting close to 1 on that. These are fractions, remember. So have planets is a fraction of and then support. So support life based on observations from things like the Kepler Space Telescope, which was one of the early NASA ones that was designed to look for exoplanets and look for life. We found quite a lot of stars have planets in their habitable zones. So we're looking at, these are Earth-like stars. You've got Earths or super-Earths. They're harder to find because they're tiny. And the systems we use, if you want to know how we do it, come and talk to me later.
I need to say something about super-Earths, but we can do it later.
Yeah. But we're starting to find stars in the habitable zone. As I said yesterday, Proxima Centauri B, which is the planet, sits in the habitable zone. It's actually a rocky planet in the habitable zone. It's a possibility.
But it's not just being in the Goldilocks zone, is it? It's got to be the right size, because the Earth and the Moon are both in the Goldilocks zone, but the Moon has no atmosphere.
That's a whole different, there's a lot of different stuff going on. It's not just a size thing, there's a lot of stuff going on with that. Potentially, maybe it could have had, but size is important because it's whether it holds atmosphere. But
because as the bishop said to the actress,
size is important, but it's not everything. As the bishop said to the actress. So what they've worked out that potentially 3 to 5 of every star that has a planet, there's potentially 3 to 5 stars that could develop life. Now, the first 2 we know. We're starting to get to the educated opinions. Okay? Because scientists will look at the data and interpret them differently. That's the wonderful thing about science, is you put 4 scientists together in a room with the same data, you get 5 different theories. All of them will be vigorously argued as theirs is the most likely. But that's how science works, because what happens is you come up with a theory, people argue about it, people eventually go, yeah, you're probably right then, and that becomes the model. In science, you have laws, they stop doing that, they call them models or theories now, because they change a lot. This is considered by some as a bit of optimistic, the 3 to 5, so it's probably a little bit less. How many of those will go on to develop life? Oh, sorry, going back on that. Between 0 and 1. At the moment, we have a sample size of 1.
You on it?
Yeah. And surprisingly, somehow, the total is 1. Because we've developed an intelligent species that can, well, we've developed lots of intelligence, but an intelligent species that can do technology.
Yeah, so I'm an optimist, and I think the number is close to 1.
Yeah.
Gary is?
I'm probably inclined to think it's like, if you're going to develop life, there's going to be some intelligent life, eventually. Again,
oh, I thought we were still on the developed life.
Yeah, developed life, sorry, yeah, developed life. So yeah, it's likely. Our planet has developed life. However, you could still argue that that's not going to happen, because we don't really have any evidence of anywhere else. It's one of the reasons we're looking at Mars, we're going to be looking at Europa. There's talk about a helicopter on Titan, because it's got an atmosphere that will support a helicopter. And Enceladus, which is pumping out organic molecules like nobody's business, is another possibility. So until we can maybe detect life out in exoplanets, we're looking here, because it's cheaper. You know, it's still several billions of dollars, but it's still cheaper than going to another planet. So yeah, between 0 and 1. May develop intelligent life, but it depends on how long life will last.
Yeah, I mean, it's sort of, I showed you all those creatures that we count as intelligent on Earth. So it's also your definition of intelligence. You know. So intelligence has evolved lots of times in different groups of animals. Therefore, intelligence is useful. Like having eyes is useful, and having a sense of smell is useful. So I think intelligence will evolve again. But whether that's as smart as a magpie or as smart as a person, you know, it's sort of conditions and so on.
One of the other problems is we've had, I think it's 7 extinction level events on our planet. It's either 5 or 7, where most of life has been wiped out. The last one is the dinosaurs, but we're overdue.
Oh no, that wasn't the last one.
Well.
Yeah. There was an Eocene mass extinction.
Okay.
There's been lots.
Yeah, we're actually going through an extinction phase at the moment.
Yes, but we're overdue for something hitting us, or that sort of level of extinction event.
Wasn't it every 120,000 years? Or
something like that. We are overdue.
The asteroid hit me, I think it's every 26 million years.
Yeah, something like that.
Was it like 8 hits and 2 misses or
Yeah,
something like that?
yeah. So we're overdue for one, and it might be that that's why we've had the time to develop intelligence. Maybe if the dinosaurs hadn't been wiped out, Harry Harrison's West of Eden might have been accurate with intelligent lizards.
Mosasaurs, yeah.
So it could be 0.0002 to 1.
And then in there is all my, and you can't be territorial, and you need overlap of generations, and you need to and all the rest of it. So
as I said, there are scientists who've looked at the equation and said, well, we need to modify this.
Yeah.
Would Yellowstone be an extinction event?
Oh God, yes.
Oh yes. If that goes. So these are the things.
It's when, isn't it?
It's when. Yeah. Yeah. There are lots of things that could kill us, not just things from space. Things on Earth could kill us.
Yeah, I mean, if Yellowstone goes as badly as it could go, it's a civilization-ending event.
Yeah.
It's not an intelligence-ending event, because there could still be, you know, people doing subsistence-level agriculture in southern Africa afterwards, kind of thing. Yeah.
But
But, yeah,
But it
they're
will
not going
affect
to
the
be
next
building
one.
radio
But it'll
telescopes.
affect the next one.
Yeah.
Probably one. Again, I remind you, all these are educated guesses. Because if we're intelligent life, the odds are pretty good we're going to be sending out signals at some point. We're going to develop the technology. Again, our sample size is 1. But they suspect that it's likely, if we reach that stage, we will send signals out. We've been doing it inadvertently without realising for a long time. And now we're doing it deliberately occasionally.
It's still a blink of an eye,
Oh,
isn't it?
geologically,
You know, I mean,
astronomically, yeah.
my grandmother was born before
Yeah,
cars and aeroplanes.
yeah.
You know, I mean, it's...
Our technology has been advancing at an unbelievable rate, and it's getting faster, which could be one of the things that wipes us out. Robots taking over the world might happen.
Yeah, but then they would send signals. So,
Yes,
you know.
they would send signals. They would be the intelligent life. Which brings us to the next one. How long? Anywhere between 304 years to 1 billion. The 304 years is based, somebody did an estimate based on the average length of post-Roman Empire civilizations. And on average, civilizations last about 304 years. Now, that's a...
I have a massive quibble about this because
Yeah.
they don't mean civilizations, they mean nation states.
Yeah.
And, you know, the Aztecs are no longer around with us, but it's not because civilization ended,
No.
it was because the
Yeah.
conquistadors turned up and
yeah.
stamped all over them.
And
you
in
know.
reality, what
Yeah.
happens is, as we've looked, if you look through the history of science, one group of people develop some science. Then, as they start to wane, another group of people take over. For instance, all the science that the Greeks developed, as the Greeks' civilization started to wane a little bit, the Arabs took it over because they translated. They developed the next stage. Then the Renaissance, the European scientists came. So they're just building on each other.
Yeah.
So that 304 is a little bit flaky, but it's a possibility that. But we could also take it up to billions of years, because if we can avoid killing ourselves, and nothing else
Yeah,
kills
and
us.
the Drake equation was written in Cold War paranoia
Yeah.
era, where everyone is expecting that either we'd all die in a nuclear war, or the Ice Age would come back and you know, grind most of civilization in the northern hemisphere into dirt underneath an advancing glacier. Now we know that we managed to delay the Ice Age coming back by, by you know, a cunning plan. Oh no, wait. And the threat of nuclear war, you know, went away for quite a while. Now Putin is waving his fist again, but you know.
But it's again, it's a educated
Yes,
guesstimate. So if we look at these, and we can plug these numbers into the equation. So if the result is greater or less than 1, it means that we're on our own. If you do all the calculations, it's great. It's less than 1.
Yeah.
It's nothing will happen. If it's greater than 1, the odds are pretty good. There are many civilizations out there. So by entering the lowest and the highest, we get that.
So that adds up to 42.
No surprise. So at the moment, by looking at the highest and the lowest, anywhere between 9.1 times 10 to the minus 11 civilizations could be out there, which means we're on our own, all the way up to 15.6 million could be out there, just in our galaxy, remember? So,
Kind of,
Just in our
I don't
galaxy.
know,
Just in
it
our
covers
galaxy.
it.
Sorry?
yeah. So in reality, we're going. The problem is that if you look at all those parts of the equation, once you get past how many exoplanets, they're going. But when you compare to what it was like in 1961, when Frank Drake came up with this equation, we have developed, and we now know 2 of them. We're getting a hang on the next one.
Yeah, the fact that we've got the 15.5 million. I've seen an estimate say 17 billion now, because
Yeah,
they've done the numbers.
yeah,
So, you know, and the fact that someone can say there might be as many as 17 million civilizations like
How
us
many stars
existing now in this galaxy. It's just
Again, that's up to debate. I've seen scientists quote anything from 100 to 400 billion. The usually accepted is about 200.
Again,
Infinite.
we don't know.
Infinite.
They're tuning it, they don't want to get in touch with us.
Thing is, I was saying to other people before, there's so many star systems within the universe, obviously, and within the galaxies.
Yeah.
We cannot be the only planet that has life.
The
I'm not
odds,
saying intelligent,
Yeah.
I'm saying life.
the odds are pretty good, I would say, that there is life somewhere out there.
yeah, it's Chris McKay of NASA, who's an exobiology expert, goes, yeah, there's life everywhere. Unfortunately, most of it will be pond scum. You know, he thinks life, easy, primitive kind of things that live in, shallow seas and ponds. Beyond that, difficult. That's his opinion.
David?
Does the modern version of the Drake equation, is it being adapted because now they're studying the light emitted by these exoplanets they're finding, and the spectrums are giving indications of the different chemicals in those atmospheres, which
Most of the modifications are pretty much what Amanda's been talking about, because the fact that we're detecting potential bioindicating gases in the atmosphere, and 2027 there's an ESA satellite being launched called Ariel, whose job is to look at about 1,000 exoplanets, so the ones we know about that exist, and looking at their atmospheres, because by looking at their atmospheres we can tell what gases are in. This is a different thing. If we can look at the gases, we can look at, well, are they life-supporting gases? Do they have oxygen and nitrogen? And there are certain gases that we call bioindicators. Things like methane, because methane in an oxygen atmosphere tends to break down quite quickly. So if there's a constant ready supply of it, it means something's producing. We call it a bioindicator not because it's pretty much a guarantee that's biological life. It could be chemical, it could be something else. But biology produces methane. Oxygen is another thing. It could be a chemical thing, but it could also be produced by biological systems.
Yeah, oxygen is very, very reactive and therefore doesn't hang around long unless something is constantly chucking it out into the...
Some of you may have seen a few years back where they got excited because of a thing called phosphine in Venus's atmosphere. It's exactly the same. It's something that doesn't hang around on its own. So if there's constant levels of it, it means something's producing it. Again, it could be some sort of biological system, but it could also be as much a geological chemical system. That's the problem with it, is we only have a vague idea, but we are looking for them. But those things we're finding are actually affecting what we can see in the Drake equation for is there a chance of life?
And scientists argue about it, and there was a brilliant talk a guy gave at Easter Court when he listed all the papers about phosphine in Venus, and he had the official long, complicated chemical title and so on, and he summarised them. Ooh, I found phosphine. There might be life on Venus. Next one. You're an idiot. No, there isn't. Oh, yes, there is. I found some more data. You didn't do your maths right. Oh, yes, I did. Oh, you didn't. Oh, yes, you did. I mean, it was just, he did it,
As I said, you put four scientists in a room, they come in with 5 theories and they'll argue about them. But the point of this is the Drake equation still useful? And the answer, as I said yesterday, is yes. Because although needs to be modified,
Embarrassing. Do apologise.
could be a word, could be one. Is it important? Yes, because it's still a tool. It was never supposed to be solved. Nobody's ever going to win a Nobel Prize for calculating it. As you can see, it's...
You lied to me. You said you'd get Nobel Prizes.
Sorry, I lied.
I don't think if you calculated it, you would get it.
Oh, yes. But the chances of calculating it, definitely in my lifetime.
Well, let's just apply some numbers then.
Yeah.
We've got it.
Well, there we go. We've just applied some numbers. You've got to justify it with evidence, unfortunately. The Nobel Prize...
You have to go to evidence.
Yeah, this is the reason that when discoveries are made, usually it takes 30, 40 years before the person gets a Nobel Prize, because you've got to prove it.
Oh, I was going to mention supergiants.
Oh, yes, supergiants,
Because
yeah.
I forgot I've got that over. Yeah, Gary, have you got your TRAPPIST thing?
Yeah.
Are any of those super...
I think there was...
yeah, get your pen picking. Do you guys know what a super Earth is?
No.
No, okay. So, Earth, underneath us, we know how big it is and what it weighs. When they've been finding...
Trappist won't be.
when they've been finding planets around other stars, there is Earth for scale, and you can see, you know, they're made of rocks and so on, but some of them are about the same size, and some of them are much, much bigger. Now, if they're much, much bigger, the gravity is going to be much, much higher. They still might be in the Goldilocks zone, they still might have water and life evolving seas like it did here, but due to the laws of physics, it is much, much harder to crawl out of the sea and adapt to life on land if the gravity is higher. Because when you're fish swimming around, the viscosity of the water and water pressure and things are far more important than gravity. You basically sort of kind of ignore gravity when you're in the water. As soon as you flop out onto land, it's much more important. And lots of things are much more difficult to do on land. And if you're going to get plants on land, they're going to be a lot tougher to eat than they are plants on Earth, because the base of the stem has to support the weight of the whole plant and so on. So there are guys that study biomechanics in biology have thought about this and going, yeah, it's going to be a lot harder to get life out of the water onto land on a higher gravity thing. It will be a lot easier for things to go back into the sea and become dolphins and whales and turtles and things. But so that might be another hindrance. So you might have your intelligent octopuses and mantis shrimps and giant prehistoric shark equivalents painfully swimming around, but land might be just algae and really tiny equivalent of centipedes and insects and what life was like on land in the very early Earth, not huge beautiful forests and savannas with majestic herds of wildebeest and all the rest of it. I mean, they might not be able to get that, So another potential, blocker.
So how important do you think, on our one example of life, do you think is our moon with its stabilising effect? Because we've kind of got a gyroscope that must help keep the Earth.
I'm not sure life would have existed without the moon.
Yeah, because tidal forces, the movement of water.
Yeah, I've seen several documentaries. Dame Doctor, she got she got a Damehood.
Is it Jocelyn Bell?
No, it's Maggie Alpling Pocock.
Oh, okay.
If you ever watch The Sky at Night, she's the really, really good. And I've seen her in real life, and she is that breathless and that excited. She is so much fun. She's a lovely lady. She did a documentary, which I think might even still be on YouTube, about what would happen if we didn't have the moon. And pretty much we've got that 23.5 degree tilt, which produces those nice seasons. Without the moon, we would spin like a top.
Yeah.
So our seasons would be chaotic. You could have a month of summer one year, and then 6 months of summer the next. It's one of the things that stabilised us. We also have the advantage of it's taken a lot of the crap a lot of the stuff that hits our Earth has actually been blocked by the moon.
But if we find life on Europa or life on Mars, then fossil life on Mars, then we know you can do it without the stabilising system. And also, there's an awful lot of stuff that is really tough. It's living in the outflow vents of hydrothermal, You think the hot water in the hotel showers is a bit too, but they're living in water that is 120 degrees centigrade. And you're going, but that's above boiling temperature. Yeah, well it is, but it's because of the pressure. It's still water. We've got some of these archaic bacteria that live in hot vents from deep sea muds and things. got into the water distillation system in our lab, in a lab in Dundee, and they just sat there in the boiling water thinking, oh, this is great, we love it here. And they could not get them out of it. They scrubbed it and changed it and cleaned it down and all the rest of it, and then they would refill it with water and switch it on again, and then these things would start growing again, because there was one little bastard somewhere that they'd missed. So there's some stuff that is really tough, but it's also not very interesting and won't be, you know, kind of holding science fiction conventions and wanting to talk to aliens.
Yeah. So it's that the moon has given us the ability to have that in that civilization, for us to allow. It's given us the time to create life and intelligent life and develop our technology.
Yeah, and we're living in an interglacial at the moment, which is also
as you can see,
useful. Not too hot, not too cold.
The Drake equation is still useful. However, there is so many hundreds of millions of variables, any one of which, if it was wrong, we wouldn't be here to have this convention. One more thing before we take questions.
Yep.
Ali is at the back. If there's anybody who's not registered for next year's convention and wants to, she has her kit, I believe. Or do you want to delay?
If the iZettle is charged up now.
Okay, so the
Okay,
iPad.
in a minute.
But yeah, so we'll take questions.
Roz?
Ross, yes.
Yes, also it's the importance of the way the structure of the planet is made up and it operates, plate tectonics.
Yeah.
I've heard it say that because we have plate tectonics and plates are always moving, that there's a constant turnover of raw materials.
Mm-hmm. Yeah.
If you
yeah,
don't have that, it stagnates. So, you know,
yeah, there are other systems like weathering of silicate rocks and weathering of phosphate rocks and so on. So it's just to quote Ben Goldick, I think you'll find it's a little bit more complicated than that. So there are other cycles, but yeah, getting stuff from spreading ridges and so on. I think, you know, the only helium we've got in seawater is coming out of volcanic vents and so on.
When it comes down to it, it's always more complicated than you think it is.
Yeah.
Louise.
I've kind of got a question. We know that millions of years ago there were like giant dragonflies and stuff like that. I mean, that was due to sort of like you were talking about oxygen and distributing it, and so I'm sure we haven't actually been able to observe any of these planets sort of scientifically, geologically, but would there be, if there was sort of more oxygen in the world, I know things would burst into flame a lot more, but would that accelerate the life process, or would it kind of actually impede it? Because or in the development of intelligent life?
I don't know. If there's more oxygen, there's a lot of biological processes you can just turn over faster, but there's always going to be choke points in things. Depending how your biochemistry is set up, you know, there's only so fast you can pump things in and out of a cell. So, but it's more like things like if there's so much oxygen, maybe you don't need red blood cells because you don't need the special pigments to carry it around. So life may not get more intelligent, it may just get lazier and churning oxygen around. I mean, that's the thing about evolution. The Hollywood idea of evolution is it produces perfection. The reality of evolution is it's a cowboy builder who's very lazy and uses substandard shoddy materials whenever he can get away with it. And therefore there will be all sorts of make do and mend. And things like electrical signals in your brain and so on, they're very expensive to do, so that we use chemical signals across nerve junction gaps. So it's expensive thing, cheap thing, expensive thing, cheap thing to send a signal, you know, from my fingertips to my brain or whatever.
It's that joke of, don't worry, I'll get to you. It's that joke of a bunch of scientists sitting around trying to work out was God a physicist or a biologist or a chemist, and they decided no, God was an engineer, because only an engineer will put a pleasure centre next to a recycling centre. Yeah.
Right, what I was going to say is, obviously a long time ago the moon was a lot closer to us.
Yep.
The days were shorter.
Yep, 10 hours.
Yep. And of course that also affected our oxygen levels and goodness as well. because the Earth was spinning faster.
Yeah, yeah, it's moving away at about an inch,
yeah.
an inch
6 centimetres.
a year, I think.
Yeah, back in the Silurian period
Yeah.
when corals first happened and they can measure the day length from the rings in the corals, the day was 22 hours long.
Yeah.
But we were basically slowing down.
Yeah,
as the,
yeah. Our days are getting longer. Eventually, in a million years' time, they'll make us work 12-hour days, because that's a third of the day or something like that. But yeah, it's slowly moving away, and the days are slowly getting longer. And it's one of the pieces of evidence when people go, oh, we never went to the moon. Yes, we did. We are firing lasers at the moon, and we are still getting responses back from the
And
reflectors.
the moon is very pissed off at it and is
Yeah.
shooting back.
We should. Then several of the Apollo missions dropped reflectors onto the moon. We are still using them. We are still tracking how far the moon is moving away from us, because we are firing things at the moon and we're reflecting it back from those reflectors that apparently you say didn't go up there.
Does that mean the Earth's not flat?
Sorry?
Does that mean the Earth isn't flat?
No, surprisingly, it's not even round, it's not even a sphere. It's a sphere with this pudgy centre. It's an oblate sphere. In fact, my favourite thing is I found out the moon isn't flat, it's egg-shaped. Because it's an oblate spheroid.
Oh God, don't remind me of that.
The side nearest us is actually bulging a little bit more than the other side because of the pull of gravity. When it was forming, the bulge was pulled more towards us. So yeah, it's even worse. So yeah, I've got 5 minutes. A few more questions? Don't forget Ali if you want to. Yeah.
Actually, speaking of the reflectors, I believe not so long ago they got a bit of a surprise because they were sending the signal up there, and they got something pinged back from something called a rover that astronauts bounced over the surface on.
Yes, yeah.
Because it had a reflector dish on it.
Yeah, there's still stuff up there, allegedly, if you believe those, the main. Yeah, if you believe the mainstream media, we went to the moon. A lot.
Wasn't there something about Io back along?
Io?
One of the moons around.
Yeah. It's the most volcanic body in the solar system. Yeah. That's because it's quite close to Jupiter and it's got an elliptical orbit, so it's all heated. Yes, at the back.
Was it last year we talked about who and what was going to the moon?
Oh yes.
Do we know the results?
Yes. Do you remember?
What's going to the moon now?
I couldn't tell you. There's still stuff going on. Do you remember I talked about last year the Japanese one that had the little toy one?
Yeah.
That went successfully to the moon. It did land upside down. What happened is as it came down, it was intended to land on a slope. It ejected the 2 little rovers. One of them was a hoppy one. The other one was the rolly one made by Tomy. But it landed and it tipped over. It was upside down. The JAXA were a bit worried, but they actually got everything back that they expected to. In fact, it lasted longer because it landed, they got a couple of weeks, then it's night time. Everything gets really cold. They weren't sure anything would come back again. Apparently, they got another set of data as well. So that JAXA one was very successful. China landed on the far side of the moon successfully, and they, I believe, are returning, or they have returned samples back to the Earth. So there's still stuff going on. NASA's main thing is looking at the manned missions, looking at Artemis and developing on from that. They're looking at, but it's a lot of it is the Indian and the Chinese and the Japanese looking at landers. So I'm not sure exactly what's still to come, but there's definitely still stuff getting ready to go. But yeah, the one with the little ball from Tomy landed successfully, got some good data, and they took photographs of each other. This is how we know that the Japanese one was lying upside down.
Gary.
Wandering around on the moon?
It did for a while. I don't think it lasted more than 2 cycles. So it's definitely survived the night and did some more. But because it gets so cold, they weren't expecting it to. So yeah, there's a lot of junk up on the moon now that's dead.
Gary,
Yeah.
as an astronomer, The debate. Pluto. Planet or no planet?
Planet.
No, no, everything about it screams not planet. I'm there with Neil deGrasse Tyson, who I know got threatening letters from 8th graders. He said the only difference between the threatening letter he got from 8th graders and those from adults is the 8th graders wrote them in crayon. The problem with Pluto being a planet is its orbit is more asteroid-like because it's highly elliptical, and it's most of the planets lie approximately on what we call the ecliptic plane, plus or minus about 8 degrees. So they're all slightly inclined. So the ecliptic plane is the plane that, if you looked at the Earth revolving around the Sun, and you took that as a plane and extended out, that's what we call the ecliptic. So most of the planets are not far off it. Pluto does that. So it goes into the Kuiper belt. It was one of the things that until 2000 and something, and I can't remember, there was no definition for a planet. And it was this conference that they decided that Pluto wasn't a planet. It wasn't the last of the planets. It was the first of a new type of planetary object, the dwarf planet. So
It's still got planet in the title.
yeah, but what happened is we discovered a whole bunch of others, and it was either, well, we make it 13 planets or we define it better. Oh, there's others. There's 5 dwarf planets.
Do we know the names of
Yes.
them? All of them?
So Ceres, which was an asteroid in the asteroid belt, is now a dwarf planet.
Yeah.
Pluto, Haumea, Makemake, and Eris. And Eris was the kicker, because Eris was believed to be bigger than Pluto. We know it's smaller, but it's more massive. So these are now the dwarf planets. So they thought it was a bigger...
Denser then.
It's denser, yeah. So it's got more, it's higher density, so it's more massive. But this was either we have 13 planets, or we say, right, we're going to develop another technology. But they had never defined a planet. Now they've defined it is, it's got to be orbiting the sun, so that gets rid of the moons. It's got to be spherical, although Haumea is sort of that sort of shape.
Well, like the Earth is.
Well, no, it's extremely that shape,
Yeah,
but it's mostly because it's spinning really, really quickly. And they have got to clear their orbit of debris, whereas Ceres sits in the asteroid belt. 3 of them sit in the Kuiper belt, including Pluto spends a lot of time in the Kuiper belt, which is a band of bodies. And Sedna is in an area we call the scattered disk, which is beyond the Kuiper belt.
So are we at risk of Earth getting declared not a planet because we're busy chucking debris out and we're not clearing it out of its
Almost
orbit?
certainly.
Yeah.
But,
well, if
I think we're done. I think we've
yes,
passed.
quick. Here's
yes.
yes. Finish it off.
Oh, well, thank you very much.